Okay, in this video we're going to do a couple of examples related to the crystal structures. Okay, specifically on the FCC. So here we are going to determine the volume of an FCC cell. Right, so the question goes, calculate the volume of the cell in terms of the atomic radius r. So what you want to find ultimately is what is volume of the cell expressed in terms of r. So it's a function of r. Alright, so how do we express this? So it's no secret that volume is, let's look at the cube. It's a cube, so each edge is labeled as A. Okay, this is A, A, A. Therefore, volume is A cube. Okay, and in the FCC section, you can pause here or go to that video if you forgot. The A can be expressed in terms of R. So for FCC, it's quite simple. We take this triangle, okay, this triangle, right? So we take that out, and this is A, and this is 4R. Where do we get 4R? Because this line is filled with atoms. So it's 1R, and then this is a whole circle, so there's 2R here, and another R. So that's 4R. And of course this is 90 degrees, and from this relation a square plus a square equals to 4r, and then I believe I've shown it in that video, a equals to 2 square root 2 r. Of course you can pause and try to work this out yourself. That will be great. So if a is this, and then you can just put that into this equation. Therefore, volume equals to 2 square root 2, hang on, okay, 2 square root 2 r to the power of 3. Okay, so expand this, let's do it slowly. So 2 to the power of 3 is 8, and then square root 2. So if you can't work it out, you can just write it one by one. Okay, that's square root 2 times square root 2 times square root 2, right? R cubed. So this square root 2 times square root 2 is, of course, 2. Now you're left with this, so that will be 16 R cubed. You can leave it as it is, no problem, as long as you get an equation for it. So when you want to find the volume of a specific material, for example, what you need to know is just the radius of its atom. Okay, we just need to know the radius of its atom, and this is pretty fixed based on what element we are talking about. Okay, of course in the slides later you'll have the full answers. Now, next is, let's calculate the atomic packing factor. So remember that the atomic packing factor is it's like a ratio. Okay, so the APF is a ratio of the atoms, or here I'm going to write the spheres, over the volume of the cell, of the cube. How much of the cube is filled with atom? And the answer will be in this form, okay, or a percentage. This is 74%. So how do we calculate this number 0.74? So that's very easy actually. So we have this equation, same as this. So what we need to find is both the Vs and the Vc. Okay, so the Vs is the volume of all the atoms. So how do we do that? We know that for FCC there's a total of 4 atoms. We calculated that just in the previous video. Okay, so there's 6 half atoms at each face, equals to 3, and there are 8 of 1/8 atoms. This is 1, therefore there's a total of 4 spheres. So we need to calculate the volume of all these 4 atoms. Okay, so for one sphere, of course, the formula is 4 over 3 pi r cubed. This is well known, I think. I hope all of you know this. So that's for one atom. So times 4, we get the volume of all the atoms in this FCC. So that's Vs. For Vc is volume of the cube. Actually, we just did this in the previous exercise. Okay, so that's this volume of the cube. So put this together in the APF equation. You find that R can be cancelled out, and you can just take your calculator and solve this. Okay, you get 0.74. So you can do the same for BCC as well. So in this table you are looking at is the whole list of a number of metals, 16 metals actually. Oops, okay, 16 metals and their respective crystal structure. Okay, so some of the structures are FCC, some are HCP, some are BCC, etc. Okay, so you might be wondering why the materials have different structure, and I'm going to leave this task to you. Okay, so after all the videos there'll be a discussion board where you'll have to do some quick research and give your input on why different materials have different structures. Okay, and of course they also have different radius. So why do you think the radius of each element is different? Okay, this is something I already expect you to be able to answer after what you learn in chapter 2. Alright, so moving on to the next calculation. So there's something called density computations. Okay, we can also calculate the density of the crystal structure. Now, density is different from APF. Atomic packing factor is simply showing how much of the cell is filled with atoms. It doesn't talk about the density. Density has a unit. Alright, density of 1 meter cube of water and 1 meter cube of oil is different because the mass is different. Alright, so density is different from the atomic packing factor, but it's the same as density that you know, which is density equals to mass over volume. So if you want to calculate the density of a crystal structure, we have to know its mass and we have to know its volume. Okay, now of course this is the cube. The mass is the mass of the atoms, right? You'll have some atoms filling up the cube, etc. And you also know, because of what you learn about APF, the mass is not filling up the entire cube. There's only mass where there are atoms. So therefore, the mass that we want to put here is equivalent to the mass of the atoms involved in the unit cell. Right? So this is mass of atoms. But in terms of volume, it actually fills up, well, it doesn't fill up the complete volume of the cell, but we are considering the structure in this form. Okay, we are not only considering a single atom, we're considering it in this repetitive form. So for volume, we are going to take the volume of the cube, which you found already in the first example in this video. Okay, so we just need to find the mass of the atoms involved in this cube and put in the volume of the cube. Okay, so if you look at this equation, it's a bit different because here the mass is further expanded into the number of atoms involved. A is the atomic weight because each element will have a different atomic weight, and Na here is Avogadro's number. So if you did your chapter 2 exercise as well, you would know how to find the mass of an atom. This is the same thing. Okay, this is chapter 2. Alright, and then once we find the mass, we can just divide it by volume. Vc is volume of the cell. Okay, let's try this on one question. Calculating the density for copper. Okay, so the element here is copper. What we need to know about copper is its atomic radius, and also it has an FCC structure, and its atomic weight, which of course you can get from the periodic table. Compute its theoretical density and compare with measured density. So whenever you see this word theoretical, it normally means based on equation. Okay, is the mathematically developed density. And the measured density, measured of course, is coming from experiment. Okay, so we will compare. Let's say we have the equation, this, and as I explained to you just now, this equation is not different from mass over volume. So you can either put it together like this, or you can calculate separately mass and volume, which I actually would prefer you do. Okay, so mass of an atom is the atomic weight divided by Avogadro's number. We did this in chapter 2. Alright, and this is mass of one atom. So to get the mass of an FCC, FCC remember has 4 equivalent atoms inside. Okay, so you need to multiply by 4, which is what we have here. 4 times the atomic weight of copper, which is our element, and the Avogadro's number. Okay, we are solving this portion. So that will get you the mass. Now be careful, since here the weight is given in grams per mole, so you know that the mass will be in grams. So normally density is expressed as kg per cubic meter or grams per cubic centimeter. So you might want to use this one because you're talking about very small quantity, right, of mass, so it's better to express it is in grams per cubic cm. So having the mass, now we need to divide it by the volume of the cell. So volume, we just get it from the, I believe, second example, okay, of finding the volume. So I'm going to take a shortcut. You have this equation for FCC volume. Just put that in, and R here, this is where you put your radius. So this is where you need to be careful. Nano is times 10 over power of minus 9. So if you want it in cm, you know you have to convert. Okay, it's better to have it in cm so that we end up with this unit. Okay, so you can pause, you can write this down if you want, and then eventually you'll get this answer. Okay, so compare it with the experimental result. So based on literature, meaning that somebody has done this experiment, they have measured the density, and they find that the density is 8.94 grams over cubic cm, so which is very close to what we get using the equation. So this is an acceptable result. Okay, I'm going to end this video here, and please look out for the coming videos and also the discussion board that we're going to have going on.